The golden ratio and its relationship to the creative process highlights the very strong connection between art and science. The underlying structures that are found in nature and the use of this ratio in art and architecture requires some fact checking, and many false impressions need to be clarified. And that's what we're about to do here. Although this is not an history of math lecture, we will begin with some basic concepts, things that you probably learned in high school. These building blocks using right triangles and ratios are closely linked to the 6th century BC philosopher and mathematician Pythagoras of Samos. He is recognized for investigating ratios and establishing foundational harmonies in musical tuning and concepts of proportionality. But most of you are probably more familiar with the Pythagorean theorem. However, it's worth noting that although the Pythagorean theorem is named after this mathematician from ancient Greece, the formula originated in India and appeared in Babylonia years earlier. While neither the Pythagorean theorem nor the golden ratio are definitively attributed to Pythagoras, there are two reasons why he is so closely linked to these formulas. First, he established the importance of proofs in arithmetic. That would later support mathematical axioms in algebra, geometry, trigonometry, calculus, and statistics. Second, credit is given to Pythagoras based on the Elements, a mathematical treatise written in about 300 BCE by Euclid. In his book, Euclid does not name the golden ratio or assign a specific number to it. That will come years later. Instead, Euclid demonstrates the concepts geometrically and describes the division of a line in extreme mean and ratio. This use of the term mean is why it is often called the golden mean. Let's break this down to math. For example, when you have a square, it's easy to figure out the surface area if you know the length and the width. A circle isn't as easy. As we know, its length and width are not measured as simple as a square would be. It requires pi r squared, 3.14. While a triangle has length and width, determining the hypotenuse isn't as straightforward. Let's explore this by calling the legs of the triangle a base and a height. The easiest way to find the surface is to turn it into a rectangle. Then you can measure the base and the height as a length and width, the same we did with the square. Once you have the area of the rectangle, divide that in half. Even with the triangle's surface area now established, we still don't know what is the hypotenuse. If you turn each leg into a square and do the same with the hypotenuse, although we don't know the measurement yet, you can still use this undetermined length to create a square. You now have 3 measurable areas. The beauty lies in this relationship. The area of both A and B equals the area of C. There you have it. A squared plus B squared equals C squared. We can now use the square root of A squared plus B squared to find the hypotenuse C. This function of the right triangles is the basis of the Pythagorean theorem and a good first step towards understanding the golden mean. Let's start with another right triangle where both legs are equal. If we take that isosceles triangle and double one length, we create a triangle with a 1:2 ratio. When we separate out the hypotenuse length and add it to the base length, we have our introduction to the golden ratio. By comparison, if we divide the length into 2 equal parts, a 1-to-1 relationship, we can see the division is close to that golden cut. Instead of a 1-to-1 relationship, we now have a 1-to-1.618 cut. That's why it's also often called the golden cut. The golden ratio is defined by the relationship where A plus B is to A as A is to B. Taking this further, we can see that A plus B is related to C, exactly as A is to B. Now, if we take these two legs and turn them into a rectangle, it's known as the golden rectangle because of the ratio of each leg. Now, as usual in math, there are multiple ways of doing the same thing. And here, there are multiple ways of arriving at the same results of the golden ratio. Here's an example beginning with a square, and happens to be the one outlined in Euclid's Elements. This rectangle is a starting point for our discussion about the subjectivity of art and how it is intertwined with the objectivity of science. This proportion is associated with harmonious aesthetic value. In 1876, psychologist Gustav Fechner tested this idea by showing 10 different rectangles to people and asked them to pick the most pleasing one. It turns out that 76% of the people selected the 5:8 ratio rectangle, which is a 1.6, very close to the 1.618 of the golden ratio. You can determine in your own life which rectangles you find to be the most pleasing. Here are a few aspect ratios commonly used in everything from photography to smartphones and laptops.
Moving from a static symmetry to a balanced, natural-looking asymmetry in pictures, photographs, and paintings, the golden ratio is often used in art. Sometimes you use a simplified version of the golden cut every time you crop a photo in your smartphone. When the golden cut is divided, we get 3 sections, and when applied vertically, it creates a grid. Modern photography has simplified the division. Instead of using the golden cut, it's reduced it to thirds. This is called the rule of thirds and serves the same purpose, helping create asymmetrical, balanced images. In addition to using vertical and horizontal lines, the golden spiral appears often in art and nature. Starting with a square, we can see that the vertical rectangle is proportionate to the larger golden rectangle. Then we can continue to divide each smaller golden rectangle with another square. From corner to corner, when you draw a line through, each place where these lines meet happen to line up perfectly with that 1.618 division. On the first square, swing an arc and continue to do this throughout the squares. Then you'll arrive at the golden spiral. Although it's just math, there's something truly unique here. That's why it's called the golden ratio. The golden mean can also be used to create other unique forms. As mentioned earlier, math offers multiple ways to solve problems. You can find the golden mean by simply drawing a star, specifically a star within a pentagon. Start with a circle divided into quarters. Take the midpoint of the half leg and connect it to the top, creating a triangle. Once you find the golden cut on the height, draw a line across where it intersects with the circle's circumference. From that point, connect the top and repeat that length around the circle to create a pentagon with 5 equal sides. Extend lines from each corner to form a star. What makes this star unique is that all its lengths are divided into the golden cut. This star became the symbol of the Pythagorean society, representing their principles. Something unique happens when the golden spiral is rotated and repeated evenly 21 times clockwise, then 34 times counterclockwise. These numbers aren't random. They're the Fibonacci numbers. So, what is the Fibonacci number? The sequence grows by adding the 2 preceding numbers. For example, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. 13, 21, 34. It keeps going until 55, 89. And guess what? This is where the Fibonacci sequence and the golden numbers coincide. This convergence of Fibonacci numbers and the golden ratio appears everywhere in nature, from a sunflower seed to seashells, pine cones, and in our body, from fingers when one makes a fist to an ear. It's even found in the Milky Way. Not just in form, but in function. Leaves on a plant rotate in a spiral that maximizes the amount of light each individual petal receives. Phi is the standard mathematical notation for 1.618, and this ratio goes by many names: the golden mean, golden ratio, golden section, golden cut, and it's also referenced as the divine proportion or sacred geometry. Similarly, the number 3.14 was first paired with the Greek letter pi in 1706, but did not become popular until Swiss mathematician Euler adopted the symbol in 1737. We've already met Pythagoras and his relationship to the golden ratio. However, the name phi and its associated Greek letter only became a standard terminology for this number in 1910, and the term was not related to Pythagoras. Phi and 1.618 were named after the Greek sculptor and architect Phidias. The Parthenon has had a complicated relationship with phi. Scholars still debate it, even though the standard term is named after the Greek sculptor. The consensus is that it was definitely not built using the golden ratio. The floor plan doesn't use the golden ratio, but the facade does. When we look at elements of the facade, please keep in mind that the Parthenon is ancient and has survived several wars. But there are a few clear examples. The width of the columns compared to the height is exactly 1.618. In the facade between the columns, there are squares. This couldn't be more evident. Between the squares are spaces that precisely match the 1.618 division. Look at them vertically and you'll see the base of the frieze, which is also broken down into exact proportion. Many people argue the Parthenon isn't connected to phi, but the facade clearly is. One more myth to debunk is the Vitruvian Man. That has nothing to do with the golden ratio. Many people assume it to be so. The drawing is based on Vitruvius, a Roman architect who lived about 1500 years before Da Vinci. The lines are evenly spaced using one consistent measurement, no 1.618 here. Although there are many other examples when Leonardo da Vinci did use the golden ratio in his artwork. In the Michelangelo painting, The Birth of Adam, there is a clear division where the hand of God touches the hand of Adam. We can see that Adam sits in a square, and the arc that is drawn is very, very similar to what we saw in constructing the golden spiral. The golden mean appears in artwork from around the world, and here's a great example of the golden spiral in the Great Wave. This also highlights the significance of wavelengths in physics and the waves that naturally embody this curve, how they move through space and with time, emphasizing the great relationship between art and science. Is there an objective perfection when there are subjective critiques of ideals? I'm sure some of you have seen beauty tips about what's the perfect face look like and what's the perfect outfit. And then there's the question, were the Greek sculptures from the Hellenistic period really ideal form? Or was Michelangelo's figures anatomically correct? What are the ideals, the standards? Can you whittle down perfection into a number, an irrational number? But as we saw, it comes pretty darn close as a beautiful proof in 1.618. The fun part of nature is that beauty is an irrational number. This irrational aspect of nature is that every single time it's slightly different. That's why we can all have golden spirals in our ears and all still look a little bit different. We might seek out perfection or think there's this idea of perfection being imposed on nature, but the reality is that's what beauty of nature is. It's about difference. It's rediscovering itself, creating itself, and being open to endless variables. That, to me, is one of these wonderful overlaps of art and science, where there's the possibility of change, of variation, of difference, imperfection, in beauty.